Okay, so now let's discuss the bound states when we have a potential with rigid walls. Okay, so here uh, let's draw the potential of this form. So this is my v of x. Okay, we'll take the potential something like this now. It's a slowly varying potential again, and this is a point. I call this x2. It's one turning point. Another turning point is here, x1. So what happens here at this boundary at x1 is that there's a strong potential over here. V of x at this region is infinity. So uh, your entire wave function will be getting failed. I mean, the wave function, whatever wave function at this region you have, will be zero at this boundary. That's what the peculiarity of our rigid wall. Okay, so in that case, how do we solve this problem? So let us put the location as 1, 2, and 3 different region, and my energy is here. This is energy, the particle. This is a classically allowed region. This is a classically forbidden region. Of course, this is classically forbidden, and yeah, it is completely forbidden as long as the potential is infinite. So what is the wave function over this region? That is not going to have any value. It's going to be zero. So indeed, at this point, whatever the boundary we have, that point, whatever wave function is there, it has to be zero at that boundary. So I'll take psi 2. Psi 2 is a wave function at this region. Psi 2 at x1. So yeah, this is my turning point, first turning point, and x1 is going to be zero, whatever form it is. So that is a condition here. We don't have a connection formula that connect between a rigid wall and uh, a case like this. There is no need of connection. It's completely zero. So boundary condition you have. What's the point of having a connection formula? So we have to use our connection formula as like the previous case. In this case, in this boundary, this is a boundary which connect uh, between a classically allowed region and a classically forbidden region. So this place we have to apply our connection formula. Okay, so what is the nature of this wave function at this location psi 2? How do we write it? Well, you can write it in terms of uh, okay, I'll write with the boundary one. So psi 2 is something, I'll take the constant right now a and divided by root p of x. I can have two components for this sine and cos in general. Sine of 1 by h cross integral that starts from x1 to x p of x prime dx prime plus a similar manner I will be having another constant, a term in cos p of x and cos. That's a complete general formula. X2 sorry x1 to x p of x prime dx prime. Okay, so this is a complete formula for my wave function. So we can use the kind of sine formula to combine the uh, provided if I am taking this amplitude constant, and even if it is not constant, you will be having a completely different constant which is coming when you are combining them. So I don't want to carry this sine and cos. whenever I have sine plus cos, I can combine them into something like sine of this quantity 1 by h cross x1 x p of x prime dx prime, plus in addition I will be having a phase. So that phase I am taking with some constant, like let's take it as beta. So when you expand it, you know you will be having sine and cos, both terms coming in. So that's a linear combination of both those terms. And you will be having, actually, if you're taking this a and this as some b, this will be some other constant c of the similar v of x, or sort of. So this is a nature of the expression. Okay. So why I'm taking sine here is that my region which from sine I can connect with an exponentially decaying solution, and I know that the solution at the region 3 is actually an exponentially decaying term. So to connect them with the connection formula, I need sine here. Okay. Now psi 2 I also will be getting in the form. So this is something that we by using the connection formula, uh, we will be having some constant. What should I take the constant? I'll take the constant as something d root p of x, some sine 1 by h cross integral x to x1, x to x2, x to x2 p of x prime dx prime, plus here we know whatever coefficient we have, as it is a connection formula, it's pi by 4. Okay, so that is your psi 2 when you are connecting it with this region, and your psi 3 is going to be some other constants e divided by root of p of x, and we have an exponentially decaying term over there, and the term is starting from 1 by h cross integral x2 to x p of x prime dx prime. That was our decaying term, psi 3. Okay. Now I have to find out this quantity first, what this beta corresponds to. See, what we have to do is we have to find out the quantization rule here. What is the quantization rule which is coming in this particular case? And to find out that, uh, uh, the thing is that we have done in the previous case exactly the same way. We have to compare psi 2. You have two psi 2's here. One is this quantity and another is this quantity. Here I don't know right now what is beta. I have to find out that, and then equate with this quantity. Then you will be getting the quantization. Okay, so how do I find out this quantity here? So you can put the boundary condition. Now connection formula, now we have boundary condition, that is much more easy. Psi 2 of x1 is equal to 0. That is a condition that we have. So the constant, you don't, no need to worry. Sine of an angle, that angle is 1 by h cross x1 to x p of x prime dx prime plus beta is 0. When do that happen? Angle is going to be equal to, this angle has to be equal to, well, n pi, right? So I can do the integration now. 1 by h cross, and this is a rigid wall. in that case, you know, P momentum, whatever value it is, that's going to be just a constant. I'm taking that constant at a particular point. Our evaluation is that's going to be constant. So 1 by h cross uh, something like a p naught. Then the integration is running from dx, and the limit is nothing but x1 to, well, x. So x1 minus x at the point again x1 plus we have a beta. So when you put this x1 value over the limit to the x, that will become 0. This quantity is going to be 0, and that indicates that your b is going to be n beta. It's a constant, right? You can choose any of the value, and the least value is going to be 0. Corresponds to n equal to 0, and you can just take that value. That means there is no phase quantity here. Beta is equal to 0. So our wave function form for psi2 will not be having this beta term. So this much only. This is our expression that we need to solve. So how do we solve this? This is psi2 equal to this expression, and psi2 equal to the bottom expression. Both are same. So equate both of them. So when you are equating that, you know their angular connection. Whenever we have something like a sine theta 1 equal to b sine theta 2, theta 1 plus theta 2 equal to n plus 1 pi if n is starting from 0, 1, 2, etc. And the amplitude connection also, you know, let's not worry about that now. Theta 1 plus theta 2. So what is this theta 1 and theta 2? Theta 1 is 1 by h cross integral x1 to x p of x prime dx prime plus integral x2 x2 p of x prime dx prime plus pi by 4 is equal to n plus 1 pi. Okay. Like the previous case, nothing else. Only the difference is that we have only pi by 4. So pi by 4, if you are subtracting from that quantity, it will become n plus 3 by 4 pi. And this is nothing but, okay, you can take this h cross here. Here I can combine the integration from x1 to x2 p of x prime dx prime. So that will give you your quantization expression for this case. X1 to x2 p of x prime dx prime is equal to n plus 3 by 4 pi h cross. So this is a quantization condition for this particular case. Okay. Now the another case is that you can always connect between this a and b by using the formula that we have already seen. So there is no need of two constant. Only one constant will be there throughout the entire wave function, because we always have the connection. And that particular quantity you will be able to find out. You can do it and find out the value corresponding to that, just a normalization. uh, then you will get the value, and it's not going to be very complicated. So okay, now another case for this rigid wall, a kind of a potential, is that both side, when we have rigid wall, what will happen? So this is at one end we have rigid wall, and both the end. So rigid wall both end, and the potential will be just like between two walls you have a potential. So here it is infinity, here it is infinity, and you have a varying potential of some sort at this region. This is your v of x. So if that is the case, what is going to be the condensation condition? See, if you know the condensation condition, you know how the energy uh, and yeah, you can calculate corresponding to each n value what is the energy from this expression. So in this case, what we will be having again here, instead of having connection formula, what we have is two boundary condition. So the same way we will get the expressions. Only thing is that boundary connection formulas are not used. You just have to use the boundary condition, and when you're putting the boundary condition, you'll get the beta in the second case also 0. So that will give you a similar uh, psi 2. Yeah, here we have beta, and here this quantity is also going to be 0. So both this phase factor will not be there in our expression. So when you're comparing them, this pi by 4 will not be coming in addition. So that will become, in the case of, so in this case our integration will become just like x1 to x p of x prime dx prime plus integral x2 x2 p of x prime dx prime. This is, that's it, equal to n plus 1 pi, which will give you x1 to x p of x prime dx prime equal to, well, what is it, h cross is 1 by h cross, 1 by h cross. So this will give you n plus 1 by h cross, where n is running from 1 2 3 etc., or you can modify. See, this is just an integral multiple. If you are okay, this here n is starting from 0 1 2 etc., 0 1 2 like that. That's the reason we took the n plus 1 by h cross, or you can write it as n by h cross, but now the n really starting from 1 2 etc. It's just an integral multiple of that quantity. So yeah, that is the difference. So that's about the bound states.